Do you now finally understand parametric equations a little better? Do you know how to go from rectangular to parametric equations or rectangular equations to parametric equations? Wait, that part maybe you don't know yet, so we're going to go over that again right now. Do you understand the benefits of a parametric equation versus a rectangular equation? Right? What's one thing that's bad about parametric equations compared to a rectangular? These are all really good things to think about as you discover more and more about parametric equations. Today we're going to talk about two things, okay? Parametrization and finding the parametric equations given rectangular. So let's see how we do that, okay? Now, part 3 on your notes. Follow along. Find the set of parametric equations to represent the graph of y equals 1 minus x squared. Wait, 1 minus x squared? We already know what that graph looks like, don't we? That's pretty obvious. If you don't know what this graph looks like, please get out. This graph looks something like this. But as we talked about, in a rectangular equation, that's all we know, the shape or the path, but not which direction or the rate. We just know that this graph looks like this. So with parametric equations, we're going to discuss what more it can do. So first thing we have to do is, if you're trying to write a set of parametric equations, you know for shizzle that you know x equals and you have to know what y equals. So that makes a set. And the x and the y talks in terms of another parameter or parameter, maybe in this case t, time. Okay? Now, in order for us to represent a rectangular equation to a parametric equation, you're right. You can set 1 however you want and then use it to find the y, or the y, what the y value should be. But in this case, t is given to us. It says x is t. Yay! So that means we're almost halfway there. X is t. So wait, y? We don't know yet, but we do know that in rectangular it's this. But we don't want to use any kind of x's, right? We want to replace the x or substitute with a t. So what do we have? Our parametric equations. Dun, 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 dun. X equals t. That's my first part of the set. And y equals 1 minus t squared. And that is my parametric equation for this particular rectangular graph, for this exact thing. If I take t, negative 2 to 2, I get this exact graph. But maybe with a little bit of more information, right? We'll talk about that later. All right, let's move on to b. Okay, how about you try b on your own? Because you're probably thinking, oh, it's pretty easy now. I kind of understand. So you're like b. T is equal to 1 minus x. But you have to write x in terms of t. Wait, did you turn off the camera? Welcome back. Okay, so now x is equal to 1 minus t. Hey, you already got x. You're halfway there. Well, you know that y is given as 1 minus x squared, so whenever you see x, substitute for t. Substitute with a t. 1 minus t squared. Now, when I do the magic here, I get 1 minus 1 squared minus 2t plus t squared. I'm going to distribute the negative nicely, but I already know that's going to produce my y value, so I'm going to go right here. X is equal to 1 minus t. What's my y? My y is going to be, well, this is going to be a gone, right? This is gone, right? And then this is going to be a positive, and this could be a negative. So I get 2t minus t squared. That's my other parametric set. Now, believe it or not, all these graphs produce this graph, but maybe slightly different. In fact, I've taken the liberty of graphing them. Dun, 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 on the bottom here. Whoa. Let's look at these. This exactly what happened is this graph here. Now, now, do these graphs look just like your 1 minus x squared? Yes, they do. Okay, yes, they do. Okay, yes, they do. But what's different? For this guy, from negative 2 to 2, it's traveling this direction. For this guy here, the part B, right? It's traveling in a different direction. What? It's same, but a little different, isn't it? Right? If this was a fly flying across the air, right? It's going to travel, one's traveling this way, and one's traveling this way. Now, I wonder the question, will they ever meet? So I could ask you that question. Will they ever meet? Are they traveling at the same rate? Clearly, they're traveling a different orientation, or they're traveling in a different, they're traveling the same path, but in a different direction, different orientation. But are they ever going to meet? And are they traveling at the same rate? These are the two questions I want you to think about, okay? So they're not the same, are they? Okay? All right. Now let's move on to the hard part. The hard part. Yeah, the hard part. Dun, 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 dun. Find the parametrization of a line through points -8, 2, 3, and 3, 6. Now, couple of key points here. Parametrization of the line through points A and B, because this next example says, find the parametrization of the line segment. And I think you know the difference between a line segment and a line. Line segment is something that ends, and line stretches on indefinitely with endpoints. This one has an endpoint because it's a line segment. And we're going to see the subtle difference between 3.2 and 3.3 example, okay? Now take a deep breath. If you need to take a break, go ahead and take a break because this is tricky-dicky, okay? Now, not really, but kind of, okay? Find a parametrization. The wording, I think, is a little bit weird, and the concept is a little bit abstract, but I think it's be easy, okay? The process is easy. Find a parametrization of a line through points -A, 2, 3, and B, 3, 6. Now, I want to put here x1, y1, x2, y2, just so we can organize our coordinates. Now, let's visualize this a little bit. I'm going to go -2, 1, 2, 3, 4, 5, 6, 7. Okay, -2, 3. That's my A, right? That's my A, okay? And that's the direction of this vector here. That's my A, okay? Where's B? B is at 1, 2, 3, and 6, right here. That's my B. So from A to B, I have that vector there, okay? But I know that they want us to find a parametrization of the line that goes through these 2 points. That means they want us to find something that goes through points A and B, but it could lie anywhere along the same direction. That means it could lie here, it could lie here, anywhere along this path. Okay? That's what it's asking for. I think the question, once you've established what the question is asking for, it should become a lot more clearer and easy. So you know what? We're going to try and pick an arbitrary point P along the path of line AB that goes through AB. So that's going to be PXY. And that's along, I'm going to, for now, I'm going to actually delete this line here so it doesn't confuse you. Okay, but you remember, it could go through here, here, anywhere along this path. Okay, but we're going to choose this specific one here. Okay, so you know what? Maybe I should put a dotted line there so you understand, right? It's going to go through that P. Now, let PXY be an arbitrary point line through AB. Okay, so that's a statement. Let PXY be an arbitrary point on a line that goes through points A and B. Okay, now a couple of facts. Let's write a couple of facts. Vector OP is OA. Oh, you know what? Let's actually just write this as a mathematical sentence, okay? Vector OP. Do you see vector OP right there? Okay, vector OP. It's right here, right? Okay. Is the sum of what? Is the resultant of what? OA plus AP. Take a look. Here it goes. OA, and then you go AP, right? But wait, some of you guys are thinking, wait, didn't it go through AB? Oh, wait. That's a really clever thing that you noticed. Because isn't OP also OA plus, wait, but I needed to get to P using B. How would I do that? Should I just multiply B by something to get to P? So I can say it's T times AB if I wanted to use AB. See if you understand that. You see how if I was at AB, I could multiply by some scalar factor, T, and get to P somehow. Yeah, okay? Okay, if this is a little tricky for you, you can ask me, question me, okay? But this is all we have to establish because we know that it's going to be some point xy, some vector xy, which is the arbitrary coordinates of P, okay? Which is equal to OA, which is -2, 3, and we have what? T plus T times AB, which is 3, 6. But wait, is AB 3, 6? Is AB 3, 6? I want you to understand why AB is not just 3, 6, okay? head minus tail. It's this, oh shoot, wait a minute, let's go back there, okay? Remember, it's this, right? So we're gonna write that as 3, sorry, okay, sorry. Let's erase that. 3 head, aiko. You think that's funny, huh? I'm sure some of you guys are cracking up. 3 minus a -2 and 6 minus 3. Head minus tails. HMT, okay? Because it's AB. Think about that, okay? So I get -2, 3 plus, can I just do the calculation right now? It's 5t and 3t. I just multiply the t. So now I'm sure you see the connection here. We already have our x component. Isn't it this and this, the horizontal component? So it's going to be 5t minus 2. What's our vertical component? Y equals this guy here and this guy, the vertical components. So it's 3t plus 3. That is the parametrization of the line through points A and B. Okay? And this is true for what? -infinity, oh gosh, -infinity all the way to infinity. Okay? Yes, fuzzy infinity to infinity, okay? That's true for any coordinates. But now, how does that change? And how do we use this part for part 3.3? Find the parametrization of the line segment with endpoints -2, 3 and 3, 6. Well, aren't these the endpoints we say? The endpoints, right? Because we know that this guy, we want it to end right here and right here. That's what the difference between this guy and this guy is. So we're going to utilize this here. So let's actually do part 3.3 above here, okay? So what does that mean? We got to figure out, so x, remember, it's 5t minus 2. So we got to figure out a new interval. T is between what and what in order for us to make this apply to the segment, line segment. So we got to see 5t minus 2, when did it equal -2? Right? So we go 5t is equal to 0. So t starts at 0 or maybe ends at 0. We'll do the next one. Well, we know that the other coordinate is a 3, right? So we're going to try this one too. 5t minus 2, it equals 3. 5t equals 5. So t must have ended at 1. Wait, what? So that means this, if we want a parametrization of the line segment with the endpoints here and here, we would say it's this exact parametric set of equations, but with the interval 0 to 1. That's the subtle difference between parts 3.2 and example 3.3. See if you understand that, okay? So wait, the complete answer for part example 3.3 is, it's this right here, okay? I'll erase these little things because that's what we found. And think about how we found this. We found the intervals by plugging into the head and the tail of points A and B, the line segment, okay? All right, now, if you don't understand some of this, try a few. This is also the example from your book, not as thoroughly described like I did in this video, but go ahead and try it. Think about it, okay? Think about the subtle difference between example 2.2 and 3.2. Now, all the this little beautiful application we're going to do in class together, so don't worry about that. For now, try some of the homework questions for this section here, okay? All right. Well, if you don't understand it completely, you can at least follow the model here, okay, to complete the assignment. Okay, good luck. Bye.